Hello, in this video we are going to look at the frequency response part 5. We will look at high pass filters and how zeros affect systems. Up until now, we are used to the fact that capacitance would allow low or will allow high pass or high frequency signals to go through. This is what we have been dealing with so far. A circuit like this, which is actually called a low pass circuit, because assuming a signal of high frequency comes in, then this capacitance would behave as a short circuit, then the output would end up being 0. In that case, the higher the frequency, the lower output we get. Now, this is the completely opposite topology. Pay attention to the positions of the capacitor and the resistor swapping positions. Assuming a signal of low frequency comes in, then this capacitor would block the low frequency and there will be no output voltage. Assuming a very high frequency signal comes in, then this capacitor would behave like a short circuit and we will have the full complement or the full value of V out. So let's use a voltage divider to explain this, just as we did for the low pass filter. So in this voltage divider, we would have R1 over the sum of the two impedances. So this capacitor would have an impedance of 1 over SC1, as we've already discussed, and the voltage divider will give the relation R1, this resistance, over the sum of the two impedances. Okay. Then it could be simplified to get this. This equation tells us a lot, but let's find the magnitude of the transfer function and replace it with omega j for a sinusoid. Now, why do we use sinusoid? Because every signal could be decomposed to a sum of different sinusoids at different frequencies and different magnitude. So it's easier to study such systems with sinusoids. Okay, now studying the sinusoid, that's replacing this S with j omega and finding the magnitude, then we are going to end up having this relation, because you would square everything here and also find the square root throughout. So that ends up giving us this. Okay, remember that j square is equal to -1, but we find the magnitude, which gives us 1. That's how come we ended up getting this expression here. So let's see what this expression tells us. This expression gives us a 0 and a pole. So what do we mean by a 0? A 0 is a frequency or a value of S, in this case omega, that will make the top part 0. And from what we see, the only value that will make the top part 0 is when the frequency omega is equal to 0. This tells us that the 0 is at the origin. So we can say that the 0 is at the origin. And what Bode's rule tells us, or Bode's approximation we could use, if the 0 is at the origin, then we increase by plus 20 decibels per decade until we get to a pole. Then when we get to a pole, we then reduce by 20 decibels per decade, in which case we are going to get a flat line again, because we're increasing by 20 decibels per decade and we reduce by 20 decibels per decade. So what will be the pole frequency? The zero frequency being 0, the pole frequency too will be the frequency that will make this term equal to 0. And if we solve that, we are going to get 1 over R1 C1, the negative. Once again, because we are dealing with the magnitude, the negative is not really important. So we know clearly that the pole frequency is going to be 1 over R1 C1. And this is how the frequency response of the system is going to be. 20 log. Okay. So clearly we see how this system behaves, and if the frequency indeed rises, what happens to the system over here? As we begin to increase the frequency, then this will no longer, the capacitance here, or the capacitor here, will no longer act as an open circuit. Then the magnitude of the output voltage would be increasing with frequency until we get to a frequency given by this, which will be a pole frequency. Then we will begin to have the full output as we expected. Okay. Now we are going to look at how we would see this in a circuit involving a transistor. So a typical example would be a circuit like this. Assuming we had some form of common source stage, so this is a CS stage, and after amplification we wanted to connect the CS stage between we wanted to connect an emitter follower, source follower, now we looked at the biasing of source followers, and in this case we could bias the source follower with I1, a current source, or some form of voltage at a point X. Now assuming we wanted to separate the DC voltage levels of the source follower from this particular emitter common source stage, then we would have to put a capacitor in between them, which is called a decoupling capacitor, and that is very useful, but it comes at a cost. And the decoupling capacitor is such that if not properly selected, then it might attenuate the signal that we seek to have here at certain low frequencies. So how do we calculate for the value of C1? We could look at a typical example here. So this is a typical question where we want to find appropriate values of C1 or Ci and values of load capacitance introduced that would be tolerated. Assuming the signal coming in is a voice band signal between 20 Hz and 20 kilohertz, what we need to do is choose values of capacitance that would not attenuate the low frequency here. So at this node, looking at the arrangement of the capacitor and the resistance from the node to ground, it looks like this node introduces a 0 into the system rather than a pole, because the zeros is such that low frequencies would be rejected, just as we have in high pass filters as shown below, where the poles, when poles are introduced, it behaves like a low pass filter where high frequencies are rejected, or high frequencies cause a reduction in the gain. But for the zero, a lower frequencies rather cause reduction in gain. So in doing the calculation, we have been given the GM, the R resistance value here as 100 kilo ohms. Then we want to find appropriate values of C1 and tolerable values of load capacitance as a result of some parasitic capacitance introduced into the circuit. So we start at the lower band. At the lower band, we know this 0 could be found by so over here so looking back at this formula, what frequency would cause the 0 not to attenuate the signal? If omega right here is equal to 1 over R1 C1, then we see that the 0 here would not cause a reduction in the gain. So exactly what we are going to do now. So we could just we could start by building a voltage divider between this impedance 1 over SCI and R, and saying we are going to get something like R1 over 1 over SC1 plus R1. Then we could simplify this to have change this to red. Could simplify this to have SC1. So here 1, we have 1 plus goes here 1 R S RC1S. Okay, then the final equation looks something like R1 C1 S over 1 plus R C1 S. Okay, then we replace S with omega J. And we find the magnitude. So by squaring and find the square root and also the absolute value. And what we are going to get is exactly what we had before. Still in a square root. Okay, so the 0 frequency we need will be 1 over omega, which is 1 over R1 C1, because this at this frequency, then the numerator would not cause any attenuation. But any frequency less than this means they are going to get a fraction, say 0.9 or 0.8 or something. That will mean there will be a reduction in the gain. Okay, so now that we understand that, then we can go back to our formula. We have 1 over R1 C1 or RICI, and the frequency of interest is 20 hertz. So we want to find out the value of capacitance that we can use to get a frequency of 20 hertz easily going through without creating any attenuation. All we will do is we just make R, which is 100,000 given in the question, K times 2 times pi, and that would give us, okay, also times the 20 hertz should be equal to C1. And after punching this on the calculator, we get the value of C1 to be approximately 79 micro nanofarad. Okay, Then let's see at the other node. So this is the other node. What do we see at this node? At this node, we also want to apply the node poles at node identification. So easily you take a node, and from the node to the ground, the capacitance, and from the node to the ground, any resistance available, then just do 1 over capacitance and resistance, the product of the two. But you need to find out whether it's going to be a pole or a zero, depending on the behavior of the circuit. Now, if a low frequency signal is coming in from this side to the node, a low frequency signal will mean there will be an open circuit here. What about a high frequency signal? Low frequency signal gives an open circuit, whereas a high frequency signal would short circuit this to the ground, which would mean the output goes to 0. In that case, this node is rather introducing a pole, because as the frequency increases, the output reduces. So the tolerable load capacitance, we wouldn't put any capacitance here on purpose, but it might be introduced as a result of parasitic capacitance, and the tolerable one, which we need, will be calculated using the same format. But this time our resistance is going to be the impedance seen at the source of this device M1, and that is 1 over GM1, and the capacitance being CL. Then we could easily rewrite it in this form: GM over CL, but we expect a frequency up to 20 kilohertz. So if the frequency goes above 20 kilohertz and is cut off, we don't really mind. But what value of capacitance would allow a frequency of 20 kilohertz to go through without much attenuation? That is what we are trying to do. So GM was given as 1 over 200 all over 2 pi times 20,000 hertz. So we have these two going and this guy coming out. Okay, so you punch this on the calculator and you are going to get something okay, approximately 40 nanofarad. So what this tells us is, if we put a capacitor of 79 microfarad here, and the load capacitance introduced is up to something like 40 nanofarad, then the signal would allow 20 hertz frequency, a signal of 20 hertz frequency, to go through without attenuation, and we could also allow a signal of 20 kilohertz to also go through the output. So we have sort of created what we call a band gap circuit, where we allow mid gap. So the frequency range that's going to be allowed is, this is 2 pi f. So 2 pi f, where f is 20 hertz, and this is 2 pi f, where f is 20 kilohertz. So the system we design, if we put a capacitor value of 79 microfarad at the beginning, C1, and a capacitor, load capacitance introduced is up to 40 nanofarad, then we could have a bandwidth or allowed frequency between 20 hertz and 20 kilohertz, which is what we call the voice band. So our voice frequency is within this range. Okay, so I hope you enjoyed this video. See you later. Bye.